Well, hi everybody, welcome back to this solder and chat version of our series. And I'm actually shooting this clip right here for the second time because when I moved the camera into its position where we're going to be shooting from, I didn't realize I kicked out the, the little power cord from my microphone, and therefore I shot that whole clip with no audio. So we're doing it a second time. What we're going to do on this video is we're going to get both amplifier modules. As you can see, we have the heat sinks off. We're going to get them both identical. We're going to put the same components on both so they match. And here's my approach. First of all, I gave a lot of thought to this bias circuit. There's been a lot of discussion on it, both in my videos, the comments of my videos, and in a lot of the forums out there as to what to do with these. My approach is going to be a little bit more of a simple one. I'm going to leave this transistor as is on both sides. They're good, they're working fine, that'll be good. This bias diode, it originally was a germanium diode. I do have exact replacement germanium diodes for this. But germanium diodes are inherently going to be unstable. They develop leakage as they age, and they're just not as good as a modern silicon diode. Now, after a lot of testing, the UF, which is a fast switching diode, the UF1004 seems to play pretty well with this circuit. That's what I'm using in this. I'll show you this, and we're going to fasten this here a little bit better later on, but it's actually in there pretty good. But with this heat shrink in here, what I've done, and I'll clean this off for you, you can see where I've cut that open so that this surface of this diode actually makes contact with the top of the transistor for better thermal contact, thermal coupling, whatever you want to call it. So we're going to go with this type of a thing. Now, I may just clean this up and use a little bit better wiring and things. We'll see. The carbon resistors are probably going to be replaced. The small signal transistors are going to be replaced because they tend to get noisy and shot noise and things like that. What I'm not going to replace is the driver transistors and the pre-driver transistors. They are in very good condition. I see no signs that they've had any kind of stress or anything, and I really don't want to ruin the look of these TO66 transistors. Of course, we could mount a TO220 modern component on there, and we could find one that would properly match. But first of all, you'd have to find a complementary pair that have the same gain range to them, which is not always the easiest thing to do, because usually the PNP side will have higher gain than the NPN when you're talking about a complementary pair. There are some out there we could find, but I like this. We're going to leave these alone as long as they're good on both sides. These are fine, they're okay. If I need to replace them, there are other replacements we can use and swap them out, but again, I don't see a need for that. And certainly we don't want to put any more variables into this already precariously designed amplifier than we have to. This thing is very susceptible, as we saw, to having values changed in the semiconductor components. So if you get a transistor that is the wrong gain range, or that is not matched properly, you can have all kinds of strange problems. And you saw where we were having problems with the DC balance control and things like that. So we're going to keep everything as stock as we can, with the exception of these transistors over here that really should be replaced because they get a lot of stress and they are very susceptible to shot noise and leakage and things like that. Had problems on the other side with those ones. Probably that means this side's going to go as well. We're going to put this little constant current source module on the tail of the diff pair. on the other side just like we did on this one. Why did I use this? Well, it's because what I had in stock and I didn't feel like reinventing the wheel. It works fine. With these two transistors like this, they kind of help each other compensate for thermal changes in here. Again, is it necessary? Can you do it with a single transistor? Yes. So this is a pretty stable little current source. It works. I've used them for a long time and they work. So we're going to do that. Replace these transistors with the same that we did on the other side and just get it generally cleaned up. So enough talking, let's start soldering. Okay, let's do a little comparison here. I have a pair of transistors that are pretty closely matched with our little VBE matching jig. And if we look up here, let me loosen the camera up, so you can see the VBE trace right here is pretty close to the line. Just a little bit, it tracks pretty good. Now, let's look at what it would look like on a curve tracer. Okay, I have the transistors mounted in the curve tracer. Now, these are the ones that we matched on the jig. And you can see, perfect match. And I did all this with just the matching jig, so I didn't even pay attention, to any of this. So you can see that there is a correlation. And let's put a pair in that are not matched and see what it looks like on our little matching jig. Okay, here's a pair that are not so well matched. And if you look, there's the trace on that one and the trace on that one. You can see there's a pretty significant difference. See that? So now let's move them over to our little matching jig. And when you look at this, the trace is actually riding above the line. Instead of kind of tracking on the line and then curving up, you can see the trace is above the line. And of course, if we turn the resolution up a little bit, you can see it more prominently. If this were a perfectly VBE matched pair, these would almost be tracking on the line until the turn on and turn off transition there. So you'd see it curve up right there, but this part of the line should track right along here, and it is not. And if you go back in the video and look at the other one, it was right on the line. So that's why I use this little jig. It's kind of quick and easy and doesn't cost thousands of dollars like a curve tracer costs. Anyway, thought you'd be interested in seeing that. Let's get these mounted up and installed in the amplifier. And just for the heck of it, let's look at our unmatched pair versus our matched pair on one of these little modules here. So this is the unmatched pair. And you can see we have 721 HFE and a 625 millivolt VBE. If we move over to this one, and yes, I'm touching these with my finger. It does make a little bit of a difference. 778 for the HFE and 626 for the VBE. So if you notice, VBE is only 1 millivolt difference. So that's how sensitive that little jig is. And here's the match set. $810 and 626. $810 and 625. So you can see just those tiny little differences. Now, would this unmatched pair work down here? Probably, because they're pretty close too. Really, we're splitting hairs. But it just goes to show how sensitive this test equipment is, both the curve tracer and our little... All right, we're going to thermocouple these. And some people think this is a necessary thing. Some people say it doesn't make that much difference and they don't care. I've gotten in the habit of doing it because I do know, as you can see on when I did the video on the little transistor matcher, especially on the Pioneer, what is it, Spec 1 video, I showed that. I kind of showed you when you put your finger on one transistor and heat it up more than the other, the difference that it makes between the two transistors. So it is relevant. So I'm just taking some regular thermal grease. Some people glue them together with thermal glue or with regular epoxy or something. The idea is just to get them to interface with one another in a way that they kind of heat up consistently with one another. So that's all we're doing here. And I'm going to take this and just I'll heat shrink it. Yes, I'm really heating up those transistors, but they're designed to take high heat like that. And they'll cool back down. Okay. So that's it. We have a thermally coupled differential pair of transistors. And then we're going to just remove the old ones. And again, these old ones on this side are still tracking pretty well. As you saw a couple of videos ago. But the other side, they went bad. So if one side goes bad, my theory is probably the other side will too eventually. So we're going to, I should probably put the light here where I can see a little better what I'm doing, huh? I don't even know if I'm on the right terminals here, huh? Okay, I think that's it. Should be able to get these out now. Yep, popped them right out. Okay, so let's form the leads on this. And excuse me if I go off frame. I have the camera like stuck in front of my forehead, kind of. And everybody's like, why don't you get a different camera stand? Well, it's not really the camera stand that's the problem. It's where you want to position the camera to be able to see everything. So that's kind of where you get into issues. Alright, so let's put this in here if I can do it. I want to kind of spin around in my fingers. Probably should have cleaned the grease off my fingers and things, the heatsink grease. But hey, what the heck. This gets boring, doesn't it? Watching somebody fumble around with all these pins, getting all 6 pins to line up is not fun. So let's get this back one in. Part of the problem is I can't get... Let's try my new, as you can see, because of some of you suggested it, it was a great idea. I went out and did it. My bench glasses. Wow, does that make a difference? Holy cow. Okay, so yeah. Look at that. I don't remember which one of you viewers mentioned this, but I owe you a debt of gratitude for that. This is great. I can see so well with this. I can't see across the room with these glasses because they're not made for that. But boy, are they good for this type of thing. Everything's just so clear. You know what they say, small things for small minds. But let's trim these down a little bit before we solder them. What do you think? We'll pop those off. If this thing quits moving on me. Okay. Just like that. I hope I'm still in camera. Yeah, I am. All right. Do this bottom one. That'll kind of lock it in so it can't wiggle around while we're soldering the other leads. All right. That appears to be pretty good. Okay. All right. That does it for our diff pair, and we know they're matched. Okay, are we in frame? All right, let's replace the inverter and the current source for the inverter. I'm calling that the inverter because that's what they call it in the service manual. Its purpose isn't just to invert the signal, that's kind of a byproduct of it, of course, but it is also to provide a gain stage for this. So you have your differential pair, and then it goes through this single inverter, which is a class A, and it provides voltage gain for the circuit. So that's what this thing's purpose is. And let's see, go over and clip these off a little bit. Like I said, I like to clip these off first and then solder them. Although it's not strictly necessary, it's nice to be able to cover over the ends of the leads with the solder, and that helps prevent corrosion from occurring. Now, something that might be interesting to look at here, let's take a look, is, once I get this soldered in here, give me a second, I want to see something. These, that looks good. These transistors, the original ones, as you can see, have gold leads on them. And one thing I was wondering is if these are just gold plated or if they're like a, I'm going to cut the end off. And yeah, they're just plated. So that plating will actually help with the corrosion as long as it's gold and not brass or copper. But you can see the cross section of it. I don't know if you can see that in there. The cross section is not. It's just regular metal. And therefore, that's why the solder helps that. The corrosion will creep right up through that and get into the transistor. I've seen it happen. So that's usually why, you know, in industrial electronics, they'll clip the leads and then solder them instead of the other way around. So let's replace the other transistor now, if I can see where it is. Looks like it's right here. Okay, so it's these three right here. Those are some pretty big blobs of solder that were on there. Okay. And we'll form this lead. Okay. See if I can get my head in the way. There we go. Just like that. And again, we'll give them a little trim. And even these silver leaded transistors are actually tinned. They have a kind of a tin coating on them to reduce corrosion. So again, they benefit also from clipping them before you solder them. Maybe I'm crazy, and you know, but I don't know. Sometimes when you do something and it works, it may be unnecessary, but you know, you never know. And if it works, why change it? Okay. So those have been replaced. Now let's look at these over here, and I'll show you what they are. These little dome transistors, I don't know if you can see them there. Those tend to go bad sometimes, so we're probably going to replace them also. Okay, this little transistor here, take it out, and it is a 2N4250. You can see right there. If we look at the schematic, this is the correct schematic, but you just can't read, but I think that says 4250. And on the newer version, they changed it to an SPS 1928, which I'm not going to. We're going to stick with what we have now. So it's a 2N. Where did I put it? 2N 4250. So the first thing we're going to do is kind of try to find a data sheet, and we'll do a preliminary, throw it in the tester and see what it does. So it's just a medium gain PNP transistor. Okay, so that's what we see so far. Now let's see if we can find a data sheet for it. Another difference I just noticed is on the first revision, which is our amplifier, the input and current source are both PNP devices, and they're, I believe, the same component. I believe they're both the 2N, 4250 or whatever they were. And we'll see that when we pull the other one out. If you look on this one, it's a different design. They're using an MPS 6519, which I have those, and which is a PNP, but on the input, SPS 1928 NPN transistor. So they made another change there. So anyway, we're just going to look and try to find something similar. The 2N 4250, which is what we have, it's not a particularly high voltage transistor. The gain for the 4250 is somewhere in that 250, and we measured that. Ours is around 250. And the transition frequency is 50 megahertz. Okay, I think we found a winner here. I have some KSC or KSA 733 CGBU, which that all means something. The C means that the collector is, if you look, it's EBC instead of ECB. And the gain range is G, which is around between 200 and 400, which our current transistor that we have is somewhere around 250, I think, 200 to 250. The voltage is 50 volts, whereas on this one it's 40, so our voltage rating is fine. Transition frequency 50 megahertz minimum, typical 180. I think this should work just fine. So we're going to try that. I do not have any KSA 992s in the F series, which all the ones I have are FBs, which are higher gain, and I think they would be a little too high gain for this. And they're also a much higher transition frequency, which I don't think that's going to matter, but you never know with these old circuits. So we're going to try these. Worst case scenario, it doesn't work, and we'll swap it with something different. I think while I'm at it here, I'm also going to remove this transistor, which I think is the same model. And if it is, then we're going to be in really good shape here. And I marked the leads because it's so easy to get that messed up. This input transistor isn't really there to make a lot of gain. It's there for impedance matching. They give it a strange name in the service manual. I forget what they call it. We'll look it up. But that's essentially it. Got those in. Flip this back over, make it look pretty. Cut the leads off again. Lovely. Okay. And let's first touch up this one that didn't need to be desoldered. And we'll go in and do these ones. This board is a little bit awkward to work on because unless you want to take all the wires off, the power wires and so forth, it's kind of tethered to the amplifier, so it would be easier if you could lay this straight on a bench, but I don't really want to take all those big wires off. And we can get to everything this way, so it's not a big deal. Okay, I believe I have this in here correctly. And if it doesn't work, well, then you'll know it's not in there correctly. Okay, so all of our transistors have been replaced, and from the previous video we replaced these couple right here that had drifted a little bit, and a couple over here. So now we're going to go through, and I want to replace this one, which is still reading good, by the way, but these carbon resistors can sometimes get noisy. The higher quality Allen Bradley ones, not so much, but we're going to replace it with modern components, and I may even have some better quality emitter resistors, these 0.15. So let's see what I have there, and we'll get those replaced. Let me do some digging. Okay, where is my microphone? Here we go. Put this on, make noise. Okay. So let's remove this 27 ohm, which is kind of in an awkward place here, but we'll get to it. All right, got that one. There it is. Okay, here we go. Like I said, I think this one is good, but if I recall, this is a 2-watt resistor. This is a 3-watt, and this one is a metal oxide or metal film, I can't remember. Definitely a flame-proof resistor, as they call them. Let's see if I bent this correctly. I did. And we'll let this sit a little bit proud of the circuit board to help with heat dissipation a little bit. That's always a good thing to do on these. All right. And what does that resistor do, you might ask? Well, it is over, let's see where it is. Right there, 27 ohm. What is it, 2 watt? You can see it right there. And that's part of your feedback for your clipping. All right, let's get this in here. Let's clip these off. Okay, kind of awkward going around those sockets, but not too bad. Like I said, once you get the heat sink off of this, it's really not that bad to work with. You just have to be careful of this little transistor. I mean, we can make something like this if we needed to, but I want to, again, keep all this stuff as stock as possible with that. Okay. Let's get some 17-volt Zener diodes, and we will replace those. Okay, our Zener diode is down here, and it is a 1N967, which crosses over to an NTE 5026A, which is a 1/2 watt 17-volt Zener diode, or Zener diode, however you want to say it. So I do have 1/2 watt 17-volt Zeners, or Zeners, or whatever you want to call them. Well, I did have them, but I set them down somewhere that I don't know where they are now. Great. But trust me, I have them. And the big thing is they're 1/2 watt. That's what I wanted to make sure. These are a little bit bigger case because they're older devices. I do not have them in 1 watt, and that was my concern. Here they are. So these are 1/2 watt. And you can see they have the same rating, but they are, case-wise, they are different size. And if I zoom you in a little bit, you can see that they are, in fact, a different size. But that's okay. As long as they're rated the same, we're good. The stripe faces out, and I'll play that back once I forget this. And again, these diodes are probably okay right now, but I don't know what it's like in the audio field, but in the equipment that I work on at work, Zener diodes tend to drift over some time. And they can drift pretty substantially, and what happens is they'll work when you first turn it on, and then after it's been running a while, they just drift. The Zener voltage will drift, and you have to replace them. I don't know if that happens on these so much or not. I know I've seen some that were out, on some of this type of gear, but again, some of this stuff, I leave it up off the board a little bit, because Zener diodes do get warm. They will, as they're doing their thing, especially when there's any kind of current involved, they'll get warm. So it's a good thing to replace them and to keep them up off the board a little bit so they can vent. And since these have a slightly smaller case than the original ones, even though they have the same power rating, they have less thermal mass than the older ones. I think this is what we want. And what we'll do is we'll get this one all fixed up and put together, and we'll test it. You can see this one's facing the other direction. And if it works very well and everything looks good, then we'll go to the other side and do the same thing to it, but we'll make sure that this side works, considering all the things we're doing to it. If you really wanted to be really careful, I guess, the better thing would be to, every time you replace a component, hook it back up and test it. But I really don't want to put the output transistors in and out 1,000 times and wear out the sockets and so forth. So as long as we get the correct components, we should be okay. I don't think we'll have any big problems, but those are the famous last words, aren't they? So let's make sure I'm still in frame here. Now, here's my thought on these wire wound resistors. Number one, I want to keep the same resistor style that we have here. And the reason being is not only do these provide current limiting for the transistors, the output transistors, that's their main function, but a secondary function is they provide some protection. If something shorts out, these resistors will burn open. If you make them the wrong type, like a flame-proof resistor or a higher wattage resistor, what's going to happen is they're going to get really, really hot, and most likely will damage the board and damage other components before they go open. So you want to stick with a wire wound resistor, and you want to stick with a 5-watt device. Now, as you recall, one side of this, which was the other side, had a faulty transistor, and although this one, the transistors were not shorted, we know that they were drawing heavy current because we had a bad component over here we had to fix, and it was causing the thing to go into protect. So we don't really know what condition these resistors are in or what they've been through. Even though they may read the correct resistance, one of them might be ready to fail. So I am going to replace them. This is not something you normally would put a priority on replacing, as long as they measure okay. But since we have them, I have these, and they are exactly 0.15 ohm, 5% tolerance, just like these. These are 10%, these are 5% here. And they're 5-watt, just like these, and they're a little bit smaller case. And we'll get them up off the board, and that should get this all ready to go. Like I said, we have them. Let's put them in. Okay, moving on to the overload / overcurrent protection circuit. And let's look at the schematic. And again, this schematic is terrible. I'll show you the other version that's slightly different than this one, but it's close. This part is very close. So we have these two transistors here that kind of monitor the current through the outputs. And one of them is an NPN, one is a PNP. Now these are not really standard transistors as per se. On this one, they're those SPS transistors. They're SPS 2324 and SPS 2325. And they also use an MPSA on the later models. I think it's MPSA 93 and 94, something like that. But what those are is those are high voltage, very low HFE or low beta transistors. And they're rated somewhere around 200 volts or so. So they're designed to take a lot of high voltage spikes and so forth, and they're not used for amplification. They're actually used in, for instance, in switching supplies and so forth. A modern equivalent that's almost identical to these is the KSP42 and KSP92 that I just so happened to have in stock, which really worked out well. There's a couple different versions of these KSPs that will work in here. The main difference is some of them are rated at the same 200 volts as these, and some of them are rated at 300 volts. They're a little bit heavier duty ones, but they all will work. So I have those here. Here's our KSP 42s and 92s, and I have one for each channel, so that's why I got two of each. And then these little 2N transistors, where are they, 2423 or 2425 or something like that? I can't remember. You can't see it. We're just going to use, these are just plain old standard transistors. We're going to use a 2N3906 for the PNP and a 2N3904 for the NPN. And I dug those out that I had in stock as well. And these are all good. These are Motorola's, these are Fairchild Semiconductor. They're all good quality transistors. And we're going to replace those. So those are located here and here. And again, they're gain matched. So you can see they have the same gain range. This one, the paint has kind of worn off. But make sure you get the same. So for instance, on this one, it's a KSP. What is it? KSP 92 TN, and this is also a TN. Those actually indicate what the gain range is going to be on them. So these are going to work just fine. So we're going to get those replaced, and then this side will be ready to put back together. And what I'm going to do before I do that is I will replace the diodes on this as well. Even though these ones are still working, I have those newer ones that are a lot heavier duty, a lot better power rating. I'll swap those out just for good measure. And then we'll put this side together. We'll disconnect power from the other side because I don't want to have to reassemble that amplifier module yet. And we'll test this and make sure everything works like it's supposed to. If not, we'll troubleshoot it. If it works, we'll kind of just check and make sure these two adjustments work as they should, and then we'll move on to the other channel. What we're going to do now is I'm going to find a way to get this fastened in here a little better. I'm going to put another drop of heatsink compound in there, and then we're going to just put a couple little zip ties on there to hold it. Forgot to turn the camera on. There we go. I'll put that on there. Okay, it may look crazy, but it will work. Now they put some kind of glue stuff on the original one, and it just kind of got crusty and came loose. So I'm hoping this will be a little bit better to keep it thermally coupled. So we'll see. And again, we may change our mind at a later date and modify this bias circuit, but I think the way it is, it should be just fine. Oh, I almost forgot. Let me get my microphone back on. We need to change these diodes while we're in here. I don't want to have to take this all apart yet again. I'm not going to pull the transformer and paint it or anything. I'll try to wipe it down with some mineral spirits or some boiled linseed oil or something. But I'm not really going to get too crazy with it because that requires a lot of unwiring of things that I would rather not unwire. So we're going to pull this out right here, and I probably should bring this capacitor up out of the way, but I'm just going to see if I can sneak in here and get these out and replaced. And I'll show you what we're going to replace them with here. Some, let's see here. We're going to use these, and these are, I don't know if they're even marked what they really are. Yeah, the P2000Ds right there. I don't know if you can read that or not, but P2000D. So let me get these out. I may have to reach in front of the camera and everything to do this, so I'll do this off camera. All I'm going to do is just grab them with pliers and just heat the joints up, take them out, and then I might take some solder wick or something, clean them up, and then put the new ones in. Okay, diodes are in. Let's start putting the amplifier back together and see if it actually works after all we've done to it, huh? Like I said, there's definitely an argument for testing these out after completely replacing each component. The issue is with an amplifier like this, the disassembly and reassembly is very, very hard on the wiring and so forth, and on this, the transistor sockets and so forth. So I would rather just be really careful with what I'm doing. And if I put a couple of problems in there, of course that's going to be more hassle to troubleshoot it for sure. But I would rather have a little extra work on my part troubleshooting than messing up the board and the wiring and all that by taking it apart and putting it together so many times. So that's what we're doing here. And we'll see if my gamble pays off or if I made a mistake. We'll see. One of the problems this thing had when it came into the bench originally is some of these sockets were not put back properly, and the screws were stripped out, and had to fix that on the sockets. So what I try to do is I'll get a long thin screwdriver like this, and I need to get the transistors. I forgot those. Hold on. Okay, and we checked the transistors on the transistor analyzer on the last video. So be sure to go back and check that out if you're interested in that. And we're going to put these on, and yes, I'm using sill pads, and again we went through all of that as well in a previous video, and I think I even put up some data sheets showing that the sill pads, in a lot of instances, if they're good quality ones, not the cheapo ones that you get 100 for $1, on eBay, but the good ones, they actually have better thermal transfer than the mica and grease, believe it or not. So that's kind of not an accurate statement when people say that these are inferior. What I will say is you have to be very careful with them because they're soft. Of course, the mica pads can crack because they're brittle. So you have to, no matter which ones you have to handle them safely or carefully so you don't damage them. But if you over tighten these, one of the problems is that you can cut through the sill pad and of course short the transistor to the socket. And I'm sure some you get really anal retentive and want to use a little torque screwdriver that measures the torque, but I don't do that sort of stuff because, well, this isn't a space probe that's going to be mission critical. It's an amplifier that's going to be in your living room. So, you know, I don't think that's just so you get them properly snugged down, you'll be good. Let's get this one in. And see, that one didn't go in straight. So I'm going to have to, there we go. That did it. You really have to watch these because they won't, you don't get them in there right. That's bad news. Okay. All right, that side is seated, so we can finish tightening it. I haven't even paid attention. Am I still on the camera? Yeah. Okay, and you can see this one's stripped. This is what happens to these sockets. And unfortunately, all of the TO3 sockets I have are just slightly different and don't fit these heat sinks or these boards properly. So you have to fix what you have. What I might do is just stand this thing up on end, and I may just put a little nut on the back of that one, which is what I'm going to do right now. Okay, hopefully you can see this. Let's turn it on. That's good. And we are not coming out of protect. Now let's see what our bias looks like right now. 2 millivolts, so it's very low. Let's see what kind of DC offset we have. Oh, it's high. So we need to adjust our DC balance. All right. Let's see if we can get the glare off of the meter. How's that? All right. Let's see if this will adjust now. Going the wrong way. Okay, this is not working at all. Something is wrong, so we will have to find out why. Okay, I have removed this transistor right here from the board. Kind of slid the soldering iron down there and kind of pulled it up through. And I sifted everything on the internet I could to get the clearest printout I could get, and I compared this to version 2, and all of these numbers right here are identical between version 1 and version 2 of this amplifier. I then took the functional diagram from the functional description section of the book, printed it out, and just kind of jotted down what the voltages should be. And this was terrible down here. This is the input transistor, and we're only supposed to have 0.4 volts, and we were getting 9 or 10. All of these numbers were messed up. This was, even though this is a voltage divider bias, this 14 volts was clear down to like 6 volts. So it got me to wondering if something's wrong here. So I removed the transistor. Now, that's where we are right now. And what I want to do is, the first thing I want to see is, do we have this voltage divider at 14 volts where it's supposed to be? And that's going to be a little precarious because I'm going to have to try to measure this. If I can move the camera where you can see a little better. It's going to be right in here we're going to have to get with the meter. So let's see if I can zoom you a little bit. It's hard to get in here at the angle we want. So it's this transistor right here, and it is the center pin. So let's turn this on first of all. Okay. Ooh, it came out of protect. All right, so let's look here. And what do I have? I'll turn the meter on, it might be handy. Let's see what we get. 14 volts. That's what we should have. Okay, let's back the camera up. And let's measure our DC offset. Look at that. 14 millivolts. Let's see if it's adjustable. Oh yeah, look at that. Wow. No offset. All right. So now let's see if we can get on to these two transistors. And we only have about 3 volts of bias, which that's fine for right now because I have it turned down. So that's good. All right. Let's see what's going on with this transistor. I wonder if I got a defective one here. All right. Put this in here. See what we get. And the transistor is good. Wait a minute. Emitter collector base. I didn't pay attention. My replacement transistor has the emitter and the collector and base swapped around. Base is supposed to be pin 2 on this one. Yep. So that being said, I have the wrong transistor in here. Well, of course, you idiot, you used a 2SA733. And remember I said the C, remember in the beginning of this? Wait a second, I said KSA733 CGBU. I was wrong. We want this to be a KSA733 GBU without the C. The C means that the collector and the base are swapped. And remember I said that, but I thought of it backwards and I never checked it. That is totally my fault. So I have to remove, that would mean that the other transistor, which is the current source, it's also going to be wired incorrectly. So now we're going to have to find a different transistor that will work for what we want. Okay, I found some MPS 6519s, which should be perfect. Hopefully the pinout is correct. Those were what were used, I believe, at least in the current source section of the second revision of this amplifier. Yep, emitter, base, collector. That's how it should be. Now the only problem is this has a little bit higher gain. We'll have to look at the specs for that, what it calls for, or if it calls. Certain ones of these transistors in the service manual are not, yeah, see, these are both around a gain of 400. They don't call for a specific gain range with certain ones of these transistors. So let's see, this one is what is it, 518 and 519, and if we look, 516 and 517, 510 and 511, but if you notice they're not calling on those ones. I'm going to have to read through this a little bit more, but I think these should be okay. Again, it's voltage. They're using a voltage divider bias on this, so I know this one won't matter. And I think this will be the same thing. It's going to be okay. So we're going to try it. I think it'll be just fine. Okay, 2N4250. Min gain is 250. Max is 700. So I think that's going to be just fine. So I guess the moral of the story is, if you have the KSA733s that are not the C version, you'll be okay. But make sure you check that. Some of the Pioneer gear that I work on uses those KSA 733s, and they have to be the C version because the two SA 733s that it replaces, they have a little bit higher voltage rating on them than, but in addition they have the lead swap like that, so you have to use the C version, and that's what those were from that I had in stock. I didn't pay attention. So that's what happens when you don't pay attention. I think you guys like watching these videos just to see me screw up. Well, what are you gonna do? I definitely won't disappoint if that's what you're here to watch. We have been so busy at work lately that it's just not even funny. And training a new employee, getting new customers, a new person in the office, just kind of everything happening all at once. It's all good stuff, but why does it all have to happen at the same time? That's the question. But I guess that's the way it is, huh? Alright, so this is now put back together. Let's bend this back up, make it look neat. Connect my ground. And then we should be able to try this out once again. Get the camera adjusted a little bit better. And let's see what we get. Put the meter over here. You should be able to see that. And let's see if we have any luck. I'm still on the dim bulb, so alright, here we go. Okay. Nice. That's what you want. 0.4 volts. Right there. And 0.4. And if we look at our 17 volt Zehners, minus 16.6 plus 16.5, that's perfectly okay. We came out of protect, and we are really good with the DC offset. That is quite nice indeed. And let's see if we can check our, let me see where I can clip onto this thing. See if we can get on to check without exploding something. Check our bias. That's a little bit low. So let's see if we can adjust that. Just bring it up to maybe 10 or 12 volts, if it will. Oh yeah, look how nice that adjusts. So I'm going to bring that up to, let's go about 12 volts. So these transistors are pretty hot, the outputs. I think we're going to be good there. Okay, that's good there. And DC offset, beautiful. 1 millivolt, about 2 millivolts. I'm not even going to touch it. Alright, let's put this back up in here in a safe place and hook up some speakers or a dummy load and see if we can drive a signal into it. Okay, we're powered up and I have 400 watts of current limiting bulbs on there. And we're turned on. I have the signal generator. I'm going to put about 400 millivolts RMS into it. Let's see. Nice. That's right at about 9 watts right there we're putting out. And of course the dim bulb is starting to light up, but because we're drawing current. But if we go here real quick, yeah, If I turn it down a little bit so it's not, that's because of the dim bulb right there, that 0.02, but that's still so low. And I mean, looking down there, we're drawing enough current to make the bulb start to glow a wee little bit. And it's actually a lot dimmer than what you're seeing in the camera. But that is very, very promising. That looks excellent. I'm going to put this side together. It's done. I'm going to call it done. All right, we're now back on the other side here. And I'm just going to start at this end and just kind of work my way back here. So I think that's almost it, right? So we have all the capacitors have been replaced. We just need to do this now. And I'll show you how I do that. Oh, and we need to put in this little module. We have the other current source. We need to take that resistor out and replace that. We'll do that momentarily. Let's get our little diode here. Okay, so I'm going to bend this over like so. So it's going to look kind of like that. Alright, so this will be the surface that'll go down here. Now, we're going to get our two pieces of wire, and we're going to stick with the same color. We're going to do blue. Actually, we're going to try to just reuse these ones if we can. Alright, because I think that'll make more sense than... Well, it looks like we've got plenty of room to do that. So I'm going to cut that off. And we're going to go to the schematic. I can measure it, but we can also just look at the schematic to see what direction these are all mounted in here. Okay. Okay, so the green, if you look here, green wire goes to the anode and the blue wire is the cathode. So the blue gets the stripe. Okay, that's what we have to remember. So we'll strip these right here. Okay. And the blue gets the stripe, so I'm going to put a little piece of tubing, Teflon tubing on there to protect it. Just to go on this one side here. And let's see, just like that. Open it up there so I can get it started. Alright, like so. It's going to go right like that. And I'm probably going to cut just a little bit off. Not much. Just a wee little bit. Snip that right about there. Put that like that. Then we're going to get another little tiny piece of that tubing. And stick it on the other end so they're even. Like so. You can see what I'm doing here. There we go. And then we're going to put that like that. So now we have those straightened out, and we're going to just trim them down a little bit. We're going to get some heat shrink tubing. Just a small couple little pieces, if we can find them. Let's see here what will work. There we go. There's one. There we go. Okay. And we're going to just snip them back a little bit. This is probably a little bit too thick, but I think it'll shrink down enough that it won't matter. Put one here. Put the other one here. And then we're just going to do a little hook on each side, like so. And again, the blue goes to the stripe, just like so. There we go. Okay, we'll tack that on there. Oh, you see what Tony did? How come you guys didn't say anything to me? Put it on the wrong one. Pretty easy to screw this up, isn't it? All right, there we go. It's not if you make a mistake, it's whether you own up to it and fix it that counts. That's really what matters. Here we go. Just like that. And then when you make double sure, yep, the blue goes to the stripe, okay. And then we do the same to this side. Okay, and I'm even still in frame, kind of, sort of. All right. Now then, move this up to here, like so.
Annie?
What?
Susie and I are going out to do.
My blushing bride telling me that she's going to the store with my daughter. Okay. Which means I will be broke once again. Okay, so now we're going to put this on like so, and kind of let it hang off the end a little bit, and then we're going to have to trim it. Just like so. And then, last but not least, we're going to take a hobby knife, these little hobby knives, and we're going to score a little bit around there. We're going to score on this, and hopefully not cut my finger off. I really need to put another blade on this thing. Next video, I'll be saying that to you again. Right? Okay. And stuff's pretty tough. There we go. So we're going to just expose a little bit of the diode so that we can get to it. Okay. We'll put a couple twists in this, and then this is going to go right down in there like so. Alright. So let's put a little bit of gobbly-goo on there. Just like that. Somewhere I have 2 more of those little zip ties. Okay, I found one. Here's the other. Alright. We will flip this over, get it down on there, just like this. Okay. And then we're going to put the little zip ties back on there. And that should hold it in place. And we will have, well, did you see what I did? I went through the lead of that capacitor. Let's try this one more once. Okay. If at first you don't succeed, screw up again, because failure is always an option. Here we go. How about that? That's a little bit better. Now I got to find another zip tie that's skinny like this one. I'll be right back. Let me get a skinny zip tie. Okay. See, I almost did it again. Good grief. Really? Wheels turning, but the hamster's dead. There it is. Okay. All right. I know some of you are biased towards germanium diodes in this instance, but I am actually a fan of silicon. I think they're more stable, more predictable, not as susceptible to leakage, and hopefully if you get one that tracks in a similar manner, which this one should, I think it would be better if I actually used those little Resistor modules I made with the little circuit board, but I didn't want to get into that on this. I think this will be just adequate for what we're doing. Okay. We want to remove the tail resistor from the diff pair. Is this it? I'll find out in a hurry. Yep, that's it. So that goes right over here to the emitter of this transistor over here. Yes. And then let's do the other side, which goes... Did I just... Yeah, I did. Haha. Took out the wrong one. It's down here. There we go. Okay. So the emitters of the transistor, we have to get this in the correct polarity. The emitters connect to the positive. So that's going to be, these are the emitters over here, and there they are tied together. So that's going to be our positive. So that's going to go this way. Okay. Get that out of there before I stab myself. Okay, let's see. I'm going to snip about this much off for starters. And then put this side on first, like that. put this one in right here. And Bob is your uncle. There we go. And we will solder those on along with the one that I desoldered in error. Okay. Now, let's put the heat sink on and put our transistors back in and see if we have success. Well, are we lucky today or not? Let's see. I have ground connected. I'm going to go on the speaker terminal, plug it in, and let's turn it on. Oh, we got a protect relay. And we're sitting at 158 millivolts. It's kind of settling. It'll take it a minute. Let's see if we can adjust it. That's really where the answer is, huh? Oh yeah. Yep, I went too far. Perfect. Look at that. Okay, let's see what bias looks like. Probably non-existent at this moment, but we'll see. Okay, millivolts. Let's set it just like the other channel. We'll go to about 12. That's good. And we'll see if it works. I guess we can put a signal into it. Let's hook up the dummy load and get everything set up. All right, connected up to the dummy load. Let's see what we get. Wow, same as the other side. Of course, we're lighting up the bulb now, and let's go back to where the other channel was. Let's look at our THD, bouncing between 0.1 and 0.2. Working just the same as the other channel. I would say we have success.